Hello there, Mr. Sutton here with the AB Calculus 4-5 Extra Practice Number 5 solutions on points of inflection. For this problem, I'm trying to find x values of inflection points for this cubic polynomial. To get that started, I need to get a couple derivatives here because eventually I want to see where the second derivative is changing signs. So let me start with f prime. That's going to be negative 3x squared plus 26x minus 56, and then that 80 just gets zeroed out because the derivative of a constant is 0. Next, I need f double prime, so that's going to be, using our power rule here, negative 6x plus 26. And then I'm going to set this equal to 0 and find some critical values. There's really only going to be one critical value since this is a first degree equation. If I subtract 26 and divide by negative 6, 26 over 6 basically is going to be 13 over 3 if I reduce that. So that's my only critical value. Let me put that on a f double prime number line and do some sign analysis around that. So first, let me test a number that's less than 13/3, like 0. And if I plug that into f double prime here, that's going to give me 0 plus 26, which is a positive. And now something bigger than 13 over 3, 15 over 3, aka 5, would do the job nicely. So here we have then negative 30 plus 26, which is going to give me a negative. Since I noticed that f double prime changes sign at 13/3, that means that f has a point of inflection at x equals 13 over 3. To find points of inflection on this one, we're going to have to look for places where f double prime is changing sign. So to do that, we have to get f double prime, but let's start with f single prime. So I'm going to have, let's see, using my power rule here with a little bit of a chain rule, I'm going to have negative 1/2 times all of this stuff to the negative 1/2. But then I have to multiply by the inner derivative, which is negative 2. So I have a negative half out in front times a negative 2 is actually going to cancel out, and we're just going to get 1 times all this stuff to the negative 1/2. Okay, well that was kind of interesting. Let's take another derivative because I need the second derivative on this one. So I've got negative 1/2 times all of this stuff to the negative 3/2. But again, I'm multiplying by an inner derivative of negative 2, so that cancels out the negative 1/2, and I just end up with all of this stuff to the negative 3/2 power. I'm going to rewrite this now in fractional radical form because that's going to make it a little bit easier to find critical values. So this is really 1 over negative 2x plus 2 being square rooted and cubed, like so. Now, in terms of places that make this either 0 or undefined, since I have a constant in the numerator, there's no way to make this 0. However, this is going to be undefined at a few places. So certainly, if I plug in positive 1 for x, that's going to 0 out my denominator, which is bad news. But also, if I plug in anything bigger than 1, I'm going to end up getting a negative being square rooted, which also is not going to work. So this does not exist. F double prime does not exist for x values that are greater than or equal to 1. So how about the values that are less than 1? Well, for values less than 1, we're guaranteed to get a positive result from this square root. And since there's nothing else to make this negative, this whole fraction is always going to be positive as long as I plug in an x value that's less than 1. Since this is always positive for everywhere that it's defined, that means there is no sign change for f double prime, and if you don't change signs for f double prime, then you're not going to have a point of inflection. On this problem, I'm given the second derivative of some function as this extremely long polynomial / trigonometric hybrid. We want to know at what x values in the interval from 0 to 3 our original graph has a point of inflection. So I need to figure out where f double prime is changing sign. So we can say that f double prime changes sign at the following x values. So I'm going to actually graph this on my calculator and then just use the 0 feature to figure out where I'm crossing the x-axis. So here we go. So here I am on the grapher in the y equals, and just to show you what I did to make my life a little bit easier, because I'm kind of lazy, I saw that I kept repeating this cosine of radical x over and over again, so I decided to write that as y1, And then for the actual function for f double prime, I'm just doing x squared times y1 minus 2x times y1 plus y1, just to save myself a little bit of entry here. I'm just going to make sure that I deselect that cosine of x, cosine of radical x kind of repeated feature there, so I'm not actually graphing it. Now I actually have to graph y2. And for my window, going back to the problem there, they said we were looking in the interval from 0 to 3. So let me go back to the calculator and go to Window, and I'm going to set my x min to 0, x max to 3, and I'll do zoom 0, zoom fit, and this should give me the perfect window to see what f double prime is doing. Now again, I'm looking for places where f double prime is changing sign. So it looks like we've got, nope, I don't know. I don't know. This looks like a bounce, not a sign change. This one is definitely a sign change. So let's take a look at what this value is. Let's look at some of the options, actually. All right, so we've got a few options here. There's a few options that have more than one sign change going on. So let's at least look at what this sign change is. Actually, let's find this sign change first, and then we'll zoom in over here just to make sure there's not multiple things going on. So we've got second trace, option 2, 0. Move my spider over here to the right. Press enter a little bit to the left of that intersection, and press enter again, and enter a third time. It looks like we're crossing at about 2.467. So that's definitely one point of intersection. Now let's look at this other intersection spot here. So let me do zoom, and I'll do zoom box, and let me just open up a box close to where that bounce is happening. I'm pretty sure we're bouncing, but I really want to make sure we're not crossing more than once. So zooming in extra close, and it's going to take a while here. Yep, this definitely looks like a bounce. Now, let's say that it isn't a bounce and it's actually crossing. That would give us not one extra, but 2 extra x-intercepts, which would mean we would have a total of 3 crossings. Since there's no answer choice for 3, I think we can safely assume that that's a bounce and not a double crossing. So because f double prime then changes sign at this value only, we can say f has a point of inflection at x equals 2.467 only. So that's going to be answer choice A. On this problem, we have the graph of f prime shown on the interval from -3 to +7, and we want to know what's true about the graph of f in terms of how many relative extrema it has, and also how many points of inflection. That's what all of these different answer choices are getting at. So for the extrema, we're looking for places where f prime is changing sign. So looking at the graph, I've got how many sign changes? Well, let's see. F prime is going to change sign. We've got 1, we've got 2, we've got 3, and although you might miss it because it's not crossing the x-axis, this jump here counts as a sign change. You're going from negative to positive. So that's actually 4 sign changes, which means that we have 4 relative extrema. Now, they didn't ask what kinds they were, mins or maxes. We just have some kind of extrema, and that's all we needed to know for this. For points of inflection, we have to look at places where f prime is changing from increasing to decreasing or decreasing to increasing, basically where f prime is reversing direction. So looking at the graph, f prime is reversing direction, changing inc to dec or dec to inc. How many times? Well, let's see here. We're going down and then we're going up, so that's 1. Here's a direction change, so that's 2, 3, 4, and this is, well, this is not really a direction change at all. So then that was a total of 4 times that we're changing direction, reversing direction, which means that f itself has 4 points of inflection. So we're looking for 4 and 4, and that would be answer choice D. On this problem, we're given a whole bunch of functions along with their first and second derivatives, so we don't actually have to find any derivatives, which is nice. And we're being asked, for which of these can the second derivative test not be used to conclude that x equals 1 is a relative min or max? So this is talking about the second derivative test and its requirements. The first requirement is that f prime of 1 has to equal 0. So we're going to have to go through and check that for all these functions. And then we have to see if f double prime of 1 is positive or negative. If it's one of those versus being 0 undefined, then we can use to conclude that we have some kind of extrema. So let's check f prime of 1 first off. So for this first function here, if I plug in 1, well, I've got 1 squared minus 1, which is 0, so that's sine of 0, which is 0. That zeroes out everything. So choice A checks out for f prime of 1 equaling 0. On to choice B for that one then. So we've got 1 minus 1, which is 0. That's going to zero everything out. So choice B checks out. Choice C now, we've got 1 plus 2 minus 3. That also comes out to 0, so C is good. And on to choice D now, because we haven't eliminated anything yet. Plugging in 1 to f prime, this is going to be 4 minus 12, which is negative 8. Plus 12 is back to 4. Minus 4 is 0. So it turns out that for all these answer choices, f prime of 1 is 0. So far, the second derivative test can be used to confirm all of them being relative mins or maxes. But now we have to plug in 1 to the second derivative and make sure that we either get a positive number or a negative number. So let's see what happens. For choice A, plugging in 1 to this f double prime gives us the following. So we're going to have to work through all this craziness. So let's see here. We've got 1 squared minus 1, which is 0. Sine of all that is going to be 0. So we've got 0 for that first term. For this next term, this is cosine of 0, which is 1, times negative 4 gives us a negative 4. So then, because this is a negative number, that shows that we have a max by the second derivative test, because you're at the, if you're concave down, you're at the top of the frown. So that's a max, relative max. So choice A, we can use the second derivative test, which means that that's not the answer choice we're going to pick. We're looking for the answer choice where we cannot use the second derivative test. So on to choice B then, plugging 1 into f double prime. So we've got 4 times or 1 minus 1, e to the 1 minus 1, plus 2 times e to the 1 minus 1, a whole bunch of plugging in here. So for this first term, 1 minus 1 is 0. That's going to zero out this whole first expression. So we move on to this one. This is 2 times e to the 0. E to the 0 is 1, so this just ends up being 2. So we have 0 plus 2, which is 2. That's a positive. So that means that we have a min using the second derivative test. If you're concave up, you're at the bottom of a frown. And now let's check out choice C. Well, this one's a lot easier to plug 1 into f double prime. You probably should have started with this one, right? Look where the light is brightest. So 2 times 1 plus 2 obviously is 4. And since that's positive, concave up, that means that f has a relative min there. So far, second derivative test can help us in all three of these cases. Let's do this last one now. We've got 12 times 1 squared minus 24 times 1 plus 12. This is going to be 12 minus 24 plus 12, all of which comes out to 0. And if you have 0, then the second derivative test is not going to help you figure out if that's a min or a max. So we don't really know what that should be based off the second derivative test, so we're going to pick choice D. For this problem, we are given the graph of f double prime on the interval from 0 to pi over 2, and we are told explicitly on this interval f has only one critical point, which occurs at pi over 16. Which statement is true about the interval from 0 to pi over 2? So we have a relative min versus a relative max, and there's also the question of whether that's also going to be an absolute min or an absolute max. So these are two separate questions. Let's first answer the question of min versus max. Since f double prime of our critical x value of pi over 16, looking at the graph, since f double prime of this is obviously a positive number, that means by the second derivative test, at the very least, since we're concave up for f, we have a relative min at pi over 16. At the very least. Now, is this also an absolute min? Well, the key here is that they said we had only one critical point. So basically, you're if this is a relative min, you're decreasing until you get here, and then since this is the only critical point, the only place where you could be turning around, that must mean you're increasing forever after. So that means that this has to be the lowest spot on the graph as well. When you only have one critical value, then you also have an absolute max or min depending on what kind of extrema you're dealing with. So, since x equals pi over 16 is the only critical point, we can therefore conclude that f has an absolute min at x equals pi over 16. So that means that we're going to pick, let's see, answer choice B. For this problem, we're given this function f, which we're told is continuous and twice differentiable, except at exactly x equals 2. And we're asked, let's see here, based off of this table of derivatives and x values, we want to know which of these statements could be false. So we're going to look at each of these and see which ones we can eliminate. So statement 1, f has a relative max at x equals 1. So let's look at what's happening at x equals 1. We see that f prime of 1 is 0, and f double prime of 1 is negative 5, which is a negative number. Well, if you have 0 for the first derivative and your second derivative is negative, by the second derivative test, you know that you have a relative max, because you're at the bottom of a frown, or the top of a frown if you're concave down. So A could not possibly be false. We're guaranteed that's true. We know the point actually exists to begin with at x equals 1 because they told us we were continuous across the entire interval. So we're not going to really be worried about any of these points not existing as a way of disqualifying having mins, maxes, or points of inflection. All right, so let's move on to option B. Function has a relative min at x equals 2. Well, at x equals 2, we don't have any information about the function. It's the derivative or the second derivative at x equals 2. Those both do not exist. What we do know is that our function is changing its first derivative from negative to positive. Since f prime changes negative to positive, and we clearly have a critical value because f prime is undefined there, that means we have a relative min, which confirms what answer choice B is saying. On to choice C. Graph has a point of inflection at x equals 3. So looking at 3, we do have f double prime equaling 0 there. So that's one condition. We also have a change in the sign of f double prime from negative to positive. So because we have that f double prime sign change, and I mean we do know that the point actually exists at x equals 3 because our function's continuous, this proves that we do indeed have a point of inflection for f at x equals 3. So by process of elimination, choice D is looking like the one we need to pick. But let's just look at it a little more closely. So graph of f has a point of inflection at x equals 4. Well, at x equals 4, f double prime is 0, so that's a good start, but we're changing from positive to unknown. Well, since we don't know that f double prime is changing signs, we cannot conclude that it has a point of inflection. It may not. It might. We can't really make a judgment call one way or the other. But this could be false. So we're going to have to pick choice D. For this calculator-based problem, I'm given the second derivative of a function, which is a pretty crazy looking thing. I'm glad this is a calculator problem. And they're saying our function has many critical points, 2 of which are at these x values. Which of the following statements are true? See, these are all asking about whether we have local mins or maxes there. So we're already given that if you plug these numbers into the first derivative, you're going to get 0 or undefined. These are critical points. Most likely 0 because this is a continuous function here. So the only question is when you plug these into the second derivative, do you get a negative or a positive? That is going to help us decide if we have local maxes or mins. So let's plug this whole thing into our calculator, and then we'll use that to evaluate f double prime of these 2 critical values. So here I am in my y equals. I've entered that whole crazy f double prime in my y1. And in case you were wondering, the way I entered this cosine squared of x is by doing cosine of x and then putting the square out here. This ends up squaring the cosine of x. All right, so let's quit out to the main screen now. And I want to plug in these 2 values. So let me first do alpha trace y1 of 2.074. and that's going to come out to about negative 5.521. So plugging that in, we get this number, which is negative. So therefore, by the second derivative test, we have a relative max, a local max, at 2.074. Next, let's try out f double prime of the other one, 7.980. And just going back to my calculator, I'm just going to arrow up and yank my input from before, and I'm just going to replace what I had before with 7.980. And press enter, about negative 21.688, if I round that off. Also a negative number, which means that f also has a local max at x equals 7.980. Looking at our answer choices, having a local max at both of these is choice D.